We're going to talk about two lens systems. I pulled this picture from our textbook where they were talking about hyperopia, which is also considered farsighted. So farsighted is when our eye itself is not focusing the light within the distance of our eyeball. So the light would actually focus at a point farther beyond the back of our eyeball, our retina. So to correct this, we need converging lens. This lens helps to start the converging of the light, and our eye finishes the converging on the retina. So in this picture, they're representing the lens here. Now the object is here. This is your book or a paper, whatever it is that you're trying to look at. If you recall, I mentioned S, the object distance, is wherever you want to hold the book. How far away from your face is comfortable? Now, it doesn't have to be a book. It could be paper. It could be your laptop, a tablet, whatever it is that you're looking at that you want to read and look at clearly. But our eyes don't see, this person's eyes doesn't see clearly at that point. The person's point that they see clearly right here would be considered the near point, where this person would actually see clearly. And so this lens in and of itself creates a virtual image farther away from the eye than the actual object. Okay, so S prime ends up being from the lens out to here. Mathematically, and in terms of what our eyes see, this image becomes the object for our eye. And so our eye focuses on this image and now creates a final image back on our retina back here that is focused and clear. So ultimately, we have light that passes through. This light comes straight through into our eyes. Okay, there is refraction that occurs. It's not like this light fully creates the image and then more light comes to create an image on the back of our retina. To mathematically deal with two lenses, the first lens is always the one the light passes through first. If we find the image of lens 1, it becomes the object for lens 2. In this example with our eye, lens 1 is our glasses, or the person's glasses. Lens 2 is the person's eye. Now the light just goes through, refracts through the glasses, refracts through the eye, and creates an image. But mathematically, we can treat the image of lens 1 as if it were the object for lens 2. When we use our equations, though, for lenses, these equations are only valid for one lens at a time. and S prime and F are all measured from the lens you're calculating for. So let's do an example. Here is an example to start with. A telescope is constructed with two lenses separated by 25 centimeters. The focal length of the objective lens is 20 centimeters. The focal length of the eyepiece is 5 centimeters. If an object is 100 meters away from the first objective lens, where is the final image of the eyepiece? And what is the overall magnification of the image? All right, so a telescope is a common example of something that would use two lenses. A nice telescope would actually use a mirror as the objective and then a lens for the eyepiece. Both of these lenses, though, in this example, are converging, and I know that based off of the values given. First of all, though, they tell us these lenses are 25 centimeters apart. The objective lens, I'm going to call it F1, has a focal length of 20 centimeters. The objective lens is whatever the light passes through first. The eyepiece, this is a little more obvious, I hope. The eyepiece is the one you look through, so the one your eye would be closest to. It tells us that this focal length is 5 centimeters. So, these focal lengths are actually right on top of each other. 20 centimeters from this lens would be here. 5 centimeters from this lens would be here. Now, both of them have focal lengths on both sides of them. All right. So, our object is 100 meters away from the first lens. So I most certainly cannot draw this to scale. I would need to draw to the left 100 meters, which is far, far away compared to my 20 centimeters and 5 centimeters I've drawn. As we approach a problem that have two lenses, we simply use the equations that we have for lenses for one lens at a time. So lens 1, pretend lens 2 isn't even there. Lens 1, we have an object way, way far away over here, 100 meters away. So the object distance, lens 1, the light from an object 100 meters away, is coming to lens 1 that has a focal length of 20 centimeters, which I'm going to put this in meters because we will need them to have the same units as we plug into our thin lens equation up here. Since I have S and F, I can find S prime. Where the image would be due to just this one lens. We will want to keep a number of decimal places. I'll show you. So I'm getting 0.2004. It goes on a few more places. Because both of these were in meters, this answer is in meters. I get a positive answer, which means this image is real, and it's on the opposite side of the lens compared to the original object. I get that off the table in the test notes. Make sure you pull that out to refer to. So this image, if I were to come up to my picture, I would measure 20, just barely over the 20 centimeters. And this is where my image would be. Its magnification, negative S1 prime over S1. So negative, we found this to be 0.2004. S1 was 100. So M1 is negative 0.002004. That means this is inverted and it's extremely small compared to the original object. We'll talk about the size in a minute. Ultimately, though, this image that we've drawn in here is now our object. Treat this image as the object for lens 2. Alrighty, lens 2. These equations up here, when we talk about S, S prime, and F, those distances must be measured from the lens we're working with, that we're doing calculations for. So since I am working with lens 2, S2 in my picture needs to be from my lens to this image that is the object for lens 2. S2, I know this distance 0.2004 is the distance measured from lens 1. But I need the distance measured from lens 2 in order to use those equations. But we know the lenses are 25 centimeters apart. So if I take the 0.25 meters and subtract the 0.2004 meters, the distance from lens 2 will be 0.049, 496. It's actually 599, so I'm just going to round right here. So just barely under 5 centimeters away from lens 2. Now we can find the image of lens 2. Same equation, but all measurements made relative to lens 2. We know lens 2 has a focal length of 5 centimeters. Now the reason I'm not rounding to 5 centimeters here is because if I did, I would get 0. Right? If I didn't keep enough decimal places, I would get 0. If 1 over S2 prime was 0, that implies S2 prime would be infinitely far away, which is not the case. I can see an image if I looked through this telescope. So keeping the decimal places is essential here. So plugging in S2 prime ends up being negative 6.187. And this is in meters because both of these F and S were in meters. what this tells me is the image, final image, created by both lenses is 6.2 meters. The negative sign means it's virtual. With lenses, virtual images show up on the same side. So this image is 6.2 meters from the eyepiece on the left side in our picture. Okay, that's where this final image will appear to be. So if we measured from this eyepiece to the left by 6.2 meters, which of course I can't draw to scale, that's where the image will be located. That's what we would see if we looked in the telescope. Now, overall magnification. We know the magnification from lens 1. The magnification from lens 2 is simply S2 prime over S2, well, the negative. So negative S2 prime was 6.187. S2 was the 0.0496. I'm getting 125 here. Now this positive sign means this image is upright compared to its object. Now recall, coming back to our picture up here, our image was inverted from the first lens. So the first lens inverted the image and made it very, very small, made it tiny. But this image right here is now our object for lens 2. So when we're looking at this magnification, the positive sign upright means this final image has the same orientation as this first image, because that's what we're treating as the object. It's 125 times bigger. So really, the overall magnification, we need to take into account the magnification of both lenses. This overall magnification actually is simply M1 times M2. So if I take 0.002004 negative times the positive 125, I get negative 0.25. This overall magnification, or total magnification, whichever way you want to state it, this means the final image is inverted. Invert. Compared to the original object. The 0.25, the final image is 1/4 the size of the original object. This is called a lateral magnification. I assume, or I would guess, that if you were to go out to buy a telescope, you would not be very excited if the box or container said that this telescope had a 0.25 magnification, because that would be really silly. The type of magnification they describe, if you were to buy a telescope, is actually called an angular magnification. So let's say with this telescope we were just working with, we were looking at a tree. And I obviously struggle artistically. So here's our tree. But we are 100 meters away from this tree. Let's say the tree was, for simplicity's sake, 4 meters tall. What we just found out is that the image we would see, let me move a little bit. The image we would see is actually, well, we have our two lenses that are 25 centimeters apart. The final image of our tree is 6.2 meters from this eyepiece. It is inverted, having an overall magnification of 1/4 means this tree would be, as far as the image we're looking at, would be 1 meter tall. Okay. See if I can actually move this up for, oops. Pardon me while I struggle a little bit with my tools. Okay. What I want you to imagine here is if I were to draw a line, this is going to be a challenge, representing going to my eyeball over to the side of the telescope. So from the top of the tree to my eye and the bottom of my tree, we'll call this a theta. If I were to do the same, let me actually do this. Finish my triangle off. There's my theta. Whereas, if I did similarly with this tree to my eye, this would be a theta prime, which I'm not drawing this very well. Ultimately, this angle, theta prime, from the top of the tree to my eye, so essentially our eye's right here, this angle theta prime is much bigger than theta. The ratio of theta prime over theta is the angular magnification. That's what would be listed on a telescope. If it's 100 times whatever it's listed at is an angular magnification. Looking at a 1 meter tall tree that's only 6 meters away is very different than looking at a 4 meter tall tree 100 meters away. It's a very big difference in distance. And so that angle ends up being very different. So we do see a magnification. It's just called an angular magnification. The lateral magnification, the one we found up here, is the measurement of the actual height of the image over the height of the object. So the overall magnification, the height of the image, that's where I actually didn't explain that. 0.25 was our magnification. The negative sign meant it was inverted. H prime, I said, let's say our tree is 4 meters high or tall. This is where I came up with the 1 meter. The image of the tree is 1 meter tall. So that lateral magnification is if we pull out an actual ruler or measuring tape and measure the actual dimensions of the tree and how big that same dimension is on the image. Angular magnification is how big in the field of view that we see the image. So even though 1 meter is smaller than 4 meters, because it is so much closer, it takes up a larger field of view and looks bigger in comparison. So we'll do some other examples. By the way, this type of telescope, if you were to use it on the ground, you do see the tree upside down and backwards, which wouldn't be terribly helpful per se. But if you're looking at the moon, for example, don't really care if you're looking at it upside down and backwards if the image is inverted. Telescopes typically will have a mirror or another lens. If we do care about seeing things right side up, then they'll have a mirror lens and that will flip the image again for us so that we can see it upright.